Ever wonder why some AI models seem to suddenly get better at complex tasks as they grow bigger? Like, how do we know if a model's improvement is real or just luck? Today, we're exploring a groundbreaking method called STEM that's helping scientists finally answer that question. Let's dive in. So here's the thing. When researchers test AI models, they often rely on benchmarks, like standardized tests for humans. But these tests aren't always fair. Some models might just be memorizing answers instead of actually understanding the material. It's like giving a student a test they've seen before and calling it a smart score. Pause for emphasis. That's where STEM comes in. Developed by a team at Beijing Normal University, STEM stands for Structured Transition Evaluation Method. It's like a detective tool that finds the magic moments when a model's performance jumps as it gets bigger. Think of it as a ladder. Some questions are easy for small models, but only the biggest ones can climb to the top. STEM tracks those tricky transition points to figure out where a model truly shines. Here's how it works. Researchers test models of the same architecture but different sizes, like comparing a basic phone to a flagship model. For each question, they track performance using a simple scoring system. 1 equals got it right. Equals tried but messed up. -1 equals totally failed. By analyzing these scores across models, they spot significant transition samples, SDS, questions where smaller models fail but bigger ones nail. These are the thresholds where a model's capabilities really take off. For example, the study found that on the GPQA benchmark, a massive model like QN3-235B didn't always beat a smaller one, QN3-8B. That's weird, right? But STEM revealed why. Some questions were just too hard for smaller models, while others were too easy for bigger ones. It's like testing a toddler on a calculus exam. They'll score low not because they're dumb, but because the test is way too tough. The real magic of STEM. It's lightweight and fast. Instead of testing a model on every question, which would take forever, researchers pick a small set of these transition samples. It's like choosing a few key puzzles that cover all difficulty levels. When a new model tackles them, its performance tells you exactly where it stands, without running endless tests. Pause thoughtful. And here's the kicker. STEM avoids the cheating problem. Traditional tests can be biased if models just guess or memorize answers. But STEM focuses on samples with clear, monotonic transitions, where performance jumps from wrong to right without zigzags. That's a sign of real understanding, not luck. So why does this matter? As AI models grow, we need better tools to measure their true capabilities. STEM isn't just a test, it's a window into how intelligence emerges in machines. But here's another twist. Even the best benchmarks have blind spots. Let's break down 3 sneaky problems that trip up even the smartest AI systems. First up, error propagation. Imagine building a tower of blocks, but if you mess up the first one, the whole thing collapses. That's what happens with AI models. If they make a mistake early in a problem, like misreading a number or misunderstanding a step, the final answer can go totally off the rails. It's like a snowball rolling downhill, getting worse the further it goes. Then there's format drift. Think of it like a recipe that promises chocolate chip cookies, but ends up with a souffle. Many AI models are trained on examples that show step-by-step thinking, like chain-of-thought prompts, but real questions don't always follow that structure. When the model expects a certain format and gets something different, it can get lost in translation. And here's a twist, overthinking. Sometimes, adding extra steps to solve a problem backfires. Like trying to calculate 2 times 6 by first converting it to binary, then solving a quadratic equation. The model might overcomplicate things so much that it introduces errors. In fact, we've seen models say 2 times 6 is 14, because they got tangled in their own logic. So what does this mean? Benchmarks, those tests we use to measure AI performance, aren't always fair. They're shaped by how questions are written. If a test favors certain formats or assumes specific reasoning paths, it might reward models for luck or trickery, not real intelligence. Music swells slightly. This isn't just about flaws, it's a chance to rethink how we design tests. After all, if we want AI to help us solve real-world problems, we need assessments that reflect the messiness of reality, not perfect little puzzles. Thanks for watching. If you found this intriguing, hit subscribe for more deep dives into AI research. Let me know in the comments, do you think AI tests should be redesigned to avoid these biases? Until next time, keep questioning, keep learning.